Usually we write it the first way because that's the way all acids are written, right? With the H at the start of the formula. So, here we've got acetic acid plus NaHCO3. Sodium hydrogen carbonate. Thank you. So, reactions, you've got an acid plus a base. You've got an acid plus a metal, and you've got an acid plus a carbonate. What do you make when you have a carbonate plus an acid? One of the things you breathe out, and one of them you drink, yeah? Yeah, you're definitely going to make CO2 and H2O and one other substance. Figuring out the other substance could be where some of you are having your difficulties. So, guess where the CO2 comes from? Which one of these two compounds on the left do you think the carbon dioxide comes from? Is it the acetic acid or is it the sodium hydrogen carbonate? It comes from the carbonate. All carbonates make CO2 and H2O. So the carbon dioxide must come from the second molecule. So this makes our CO2. What is left in that formula once you take the CO2 away from sodium hydrogen carbonate? What's left? What letters? Na, H, and O. So that's what's left from that compound. What do all acids do? Bronsted-Lowry definition. Acids are, Andrew? They give up their hydrogen ions. So our acid is going to give us our other H to make water. So H and an HO will give us the water. So that's where the CO2 and H2O come from. The H from your acid, the second O from your carbonate, and in this case, the H from your carbonate as well. All right, that leaves sodium and whatever's left from our acid. Which one's going to go in the front of your formula? The sodium. And then what is left from your acid is C2H3O2. So you make carbon dioxide, water, and sodium acetate. Acetic acid, acetate ion. Okay? So this is acetic acid. This is an acetate ion. So it is the formula for your acid, and you take away an H, and you give it a -1 charge. So what you'll have left, and you're going to know what it's called in a minute, but what you have left from your acid has a -1 charge. If you lose 2 H pluses, it's got a -2 charge. If it loses 3 H's, it's got a -3 charge. Okay? So I think the question says, why is this a green alternative? Green products are considered to be products that are not corrosive, harmful to your health, or harmful to the product that you're using it on, like your sinks. So all bases are corrosive. All acids are corrosive. But vinegar is so dilute, you can put it on your food. So we use it on French fries. You can find it on salt and vinegar chips. So you can eat it. And baking soda, sodium hydrogen carbonate, you can use it in baking, right? You put it in baking products when you bake because that makes everything airy, right? Gives the bubbles so you're not eating a rock hard cake. It's because of the baking soda in it, because it makes carbon dioxide, bubbles of gas. So it pushes it up. All right, so this would make bubbles of gas that hopefully would move whatever's stuck down your drain instead of eating away at whatever is stuck in your drain. So it's considered a greener alternative because it's not as harmful to you or to the environment. So first example, we've got acetic acid. Plus water, double arrow, hydronium ion, and the acetate ion. Do you know how to spell hydronium ion? There you go. The hydronium ion is what you call the H3O plus. All right. What in here differs only by an H plus? And? Acetic acid and C2H3O2, right? The only thing they're missing in their formula is an H with a plus charge. The plus cancels out the -1 charge. So these are conjugate acid-base partners. How about water and hydronium? Do they differ in their formula with an H plus? Yeah, so those are also conjugate acid-base partners. So you link them like that, and then we label them. On the left side of your arrow will be your acid and your base. On the right side of the arrow will be its conjugate partner. So these will be acids and bases, and this side will be its conjugate partner. So if you're a base on the left, your partner is a conjugate acid, and if you're an acid on the left, your partner is a conjugate base. So left side of the arrow are your acid and your base. The right side of the arrow are the conjugate acid and conjugate base. So who on the left gave up an H? The acetic acid, right? So this is your acid. That's your acid. So that makes its partner a conjugate base. So what did water do? Did it donate an H plus or accept an H plus in this reaction? Donate. H2O? It accepted an H plus and became H3O plus. So this accepted, so it's a base. That makes this half, bless you, conjugate acid. some of you, well, some of your peers, last period, they got the first one, the acid and the conjugate base. If that's the conjugate base, that means that has to be the conjugate acid, which means that has to be the base, so they worked backwards. You will have two pairs in your formula. You will have an acid and a base. Therefore, you will have a conjugate acid and a conjugate base. All right, try the next one by yourself. Connected.
NH3 and NH4.
Let's go.
And?
And H2O and OH.
You got it. So that's the first step.
So then NH3 and NH4, A, and then CB.
So A here, CB here.
Yeah, in other words, B and CA.
Okay, so my question to you is, what happened to ammonia? What happened to NH3?
It gained.
It gained. So is
The
that an
other
acid
one
or a base?
donated.
Yeah, so does that make ammonia an acid or a base if it gained an H?
A base.
It makes it a base. So flip these.
Oh,
So this is actually a base, and that's a conjugate acid, which means your water is your acid and your conjugate base. Your, right? Yes? No? Do you get this? No, not at all? NH3 went to NH4
Yeah.
plus, so it gained an H.
Okay.
So when you gain an H,
Oh, yeah.
you're a base. So that's why it's got to be. Okay, all right. Okay, so it says, what would be the conjugate acid for the following? So if we're looking for a conjugate acid, what are they acting as? They're the bases, right? So what would be the conjugate acid? So these are bases, so we're looking for the conjugate acid. What does a base do? It accepts. So all of these all of these bases will accept NH plus to make their conjugate acid. So what would this be? It was HCO3 1 minus. If it gains an H plus, H2CO3. Okay, let's think about that. I gained an H, and it has a +1 charge. +1 plus -1 is 0, so there's no charge. So this is the base, this is the conjugate acid. Bases will accept an H. So then, SO4 2 minus? Ooh. HSO4, and what's the charge? 1 minus. I have two negative charges, I add a positive charge, so it is only 1 negative. So there's my base and its conjugate acid. So OH minus accepts an H plus to become H2O.
No charge.
No charge.
Doesn't that,
Go ahead.
you see, I think at sulfate, when you put in H to make it balanced, shouldn't you do H2 as well?
No, I'm not making it balanced, I'm adding an H plus.
So it doesn't matter if it's balanced or not.
You only add one H. Conjugate acid-base partners differ in formula by one H. That's it, no more H's, okay? All right, so what are the conjugate bases for the following? So that means they are acting as acids. So H3PO4, what's its conjugate base? H2PO4 with one negative. If I lose another H, if I do the conjugate base for this, it would be HPO4 2 minus. Okay? All right, so HSO4. So now it would be 2 minus, yeah. Right? It's acting as an acid.
Oh, it lost one.
Wait a sec. Yeah, so it lost one. All right. HOCN is OCN with a -1 charge.